Modern intelligence analysis does not suffer from a lack of information. The failure point is entirely the opposite, a crippling excess of data. Analytical divisions are currently drowning in what we call an information tsunami. When border security units intercept contraband networks or human trafficking rings, physical seizures translate into massive digital evidence. We are looking at gigabytes of raw data pulled directly from the smartphones of targets, alongside sweeping open-source intelligence polls. This is not cleanly organized intelligence. It is a chaotic web of unformatted Telegram histories, disjointed Viber chat logs, and fragmented communication threads. Expecting a human analyst to manually read, categorize, and extract actionable insights from tens of thousands of messages is a mathematical impossibility. By the time an officer finds a critical connection, the operational window has already closed. The sheer volume of unstructured digital evidence renders traditional manual analysis entirely obsolete. The obvious technological fix to this volume problem is artificial intelligence. Public chatbots and commercial large language models could process these logs in seconds, but deploying them is strictly forbidden. Feeding operational data into a public, cloud-based server creates the severe vulnerability in operational security. You are essentially handing sensitive intelligence to a third-party corporation. This diagram illustrates the problem. Uploading border intelligence to external servers is a direct violation of state secrecy protocols and personal data protections. The cloud is a hard red line. The solution is to bring the processing power inside the perimeter. We deploy a local large language model. This is a fully autonomous AI engine. It runs entirely on the agency's proprietary physical servers, completely disconnected from the open internet. True analytical velocity is only possible when advanced AI processing is deployed behind an impenetrable digital air gap. We begin the processing pipeline with the raw input, gigabytes of casual, unstructured chat logs extracted from a seized device. The analyst's objective is to strip away the conversational noise and locate specific operational indicators. This diagram demonstrates the first technical solution, utilizing the local LLM for named entity recognition. The analyst prompts the model to scan raw text and extract geographic coordinates. Simultaneously, it isolates physical asset data, like vehicle license plates. Finally, it targets the cryptocurrency wallet addresses used to facilitate shadow payments. An automated pipeline executes this entire extraction in seconds. A human analyst would spend days manually reading the same text to find these exact data points. Named entity recognition transforms unstructured digital noise directly into queryable, high-value targeting data. Phase 2 involves processing intercepted communications written in foreign languages. Standard offline translation software fails when applied to operational data. It provides literal translations that miss the nuance of the conversation entirely. Transnational criminal networks deliberately employ highly specific, localized slang to obscure their logistics and mask their intent. This animation illustrates the local LLM's unique semantic capability. We feed it a block of foreign text mixed with unknown symbols and trigger offline processing. Instead of a nonsensical literal translation, the model generates a context sidebar. It explains the hidden meaning of the specific jargon, outlining its actual criminal definition based on context. This deep semantic decryption happens entirely offline. The open internet is never pinged, and the air gap remains intact. The local LLM operates as an embedded cryptographer, decoding hostile intent without risking digital exposure. Phase 3 addresses an internal logistical challenge, aggregating diverse daily field reports from border patrols. Border guards at physical checkpoints generate constant streams of textual notes, explanations, and instant reports. These are entirely freeform and vary wildly in detail. To properly assess threats, this data must align with the Common Integrated Risk Analysis Model, or CIRAM 2.0, the standardized framework required for European border security. Manually rewriting hundreds of unstructured field notes to comply with strict CIRAM formatting creates massive administrative friction. This diagram demonstrates the automated pipeline normalizing data. The LLM processes the messy report and instantly restructures it into a strict JSON format. It automatically identifies and maps the text into the 4 mandatory pillars: time, place, actors, and modus operandi. Automated standardization removes the administrative burden, making raw field data instantly ready for database ingestion and long-term trend analysis. Phase 4 brings us to multi-source synthesis. This is the highest cognitive hurdle for any intelligence analyst. Consider a complex investigation into a sophisticated illegal border-crossing scheme, such as the abuse of a commercial transit registry. The evidence for this investigation is highly fragmented. The analyst reviews written witness statements, raw financial records, and distinct transit databases. Holding all of these disparate data points in human working memory simultaneously to find a correlation is incredibly difficult. This diagram shows the LLM functioning as a cognitive co-pilot. We input document A and document B, and the model establishes a neural link. By cross-referencing the text in its context window, it surfaces non-obvious timeline overlaps and identifies shared actors across entirely different datasets. This process requires a human in the loop. The AI merely flags the anomaly. It is the human analyst who verifies the connection and confirms the intelligence. Multi-source synthesis frees the analyst from being a manual data aggregator, allowing them to operate strictly as a high-level decision-maker. The final bottleneck in the intelligence cycle is communicating the processed findings upward to leadership. Analysts face a daily burden of repackaging complex operational data into concise executive briefs. We apply a technique called smart summarization to the daily logs of border anomalies. This animation shows the entire pipeline in action. The analyst prompts the model to compress massive weekly incident logs into a precise 500-word executive summary, highlighting only the critical threats. Automating the reporting cycle directly accelerates the speed of executive decision-making. We return to the core challenge. Intelligence divisions must process massive data volumes while maintaining absolute operational security. Relying on public cloud infrastructure is inherently incompatible with the protocols of a state security apparatus. A localized AI architecture solves this. It guarantees full data sovereignty without sacrificing processing power. Deploying a local large language model is an absolute strategic necessity for future-proofing intelligence divisions and our national security. Analytical dominance in law enforcement now requires possessing cutting-edge artificial intelligence that remains 100% under sovereign control.